All right, it's a pleasure to introduce our next speaker, Dr. Joachim Vandekerckhove, and I apologize if I didn't get it quite right, from the University of California at Irvine, who's going to talk about statistical power and its role in evidence in the psychological literature in particular.
Thank you for that introduction. And I'd also like to take a second to thank the organizers for the invitation and for putting this together. This has been one of the most interesting meetings I've been to. And one interesting observation, at least, I imagine most of the audience has made, is that many speakers are talking about the same things and bringing the same message and drawing the same conclusions, which is not immediately given because it's a very diverse audience or a very diverse group from different fields, not just, so being in the life sciences and the social sciences and in medicine. My talk will be focused a little bit on the psychological literature, on the social sciences, but that is almost exclusively, I think, because the first sort of big replication study or reproducibility study was done in psychology, or the one that became somewhat famous in 2015. So if you haven't heard of this, I imagine most people in the room have, but the Reproducibility Project, Psychology, is a paper that was published in 2015, but a project that took quite some time. I imagine Brian Nosek will talk a little bit about it tomorrow. The Open Science Collaboration is a group of something like 270 plus scientists who got together and tried to systematically replicate a large number, so 100 studies chosen from leading journals in the field, published in a particular year, to be a sort of unbiased set of original studies that they would attempt to replicate. And what they did, just to make sure that they made a sort of a reliable, trustworthy case, was they pre-registered this set of replications. So they said in advance, these are the things we'll try and replicate, just so they wouldn't be tempted later on to publish or to talk only about those things that worked or studies that fit some sort of criterion. So they would avoid selection bias and publication bias. And that's a great thing, and I'll get back to why that's true in a minute. But once the project was finished, so an obvious statistical question arises, so which of these 100 studies replicated? It turns out that that's not a trivial assessment to make. In no small part, because not everyone agrees what constitutes replication success. So when does something replicate? What should be your metric is not obvious. And one overarching question that makes this not obvious is, are we interested in testing theories or hypotheses? So a hypothesis proposed and tested in a particular study is a derivation of a theory. It's very narrow, and people who publish scientific papers often test hypotheses that are theories that live in a very narrow space. So their claim is, in these circumstances in the lab, A will be greater than B, or C will be equal to 0, or something like that. But very often when we think about replication, we think this should be a test of the same theory, the same concept under different circumstances should replicate. Nevertheless, when we assess replication, we very often think only about hypotheses, especially when statisticians become involved or people who try and fit some sort of formal method on top of this. It's much easier to think about hypotheses because theories tend to be somewhat underdefined. It's not obvious from a paper what the scope of the claim is, whereas the hypotheses tend to be well defined. So one way of evaluating whether a study is replicated or whether a result is replicated is to compare whether the new data, so the data in the replication, are better represented by a theory that's informed by the old data, so a hypothesis, that's informed by the old data versus a null hypothesis that says there's no effect going on. So you can compare these two, and you can compare which one gives more support to the new data. You can show that in a little figure like this and ask, well, do the new data, so that black little square, do they look like they are reasonably a draw from a theory or a hypothesis that's generated by the original data, which is the blue distribution, or do they look more like they're a draw from the null hypothesis, which is orange? So in this case here, the data clearly fall in the blue end, so this would be considered sort of a successful replication. The data are more consistent with the original claim than with 0. Whereas this would be a more ambiguous claim where the new data seem to fall more closer or are more supported by the null hypothesis than by the original hypothesis. So you can do this for each of the 100 studies, and you get something like this. This isn't all of them. This is a subset for which that calculation was easy to do. But what you get, and I'm not going to go all the way through this, but I've ranked them from most clearly replicated to most clearly not replicated. And what you get is some fraction that's somewhere around a third of studies appear to replicate, appear to give the same result in the replication than in the original, and the rest apparently don't. Now, like I said, there are multiple ways of testing whether something's replicated, but per the original authors and per this quick analysis, something like 35 to 40% of these studies replicate successfully. My claim towards the end of the talk will be that this is an insufficient way of looking at the data. Reactions to this project being published, this came into the media and the reactions were swift. There were some that were sort of dry results. Smithsonian Magazine and Times Higher Education sort of reported on this. More than half of psychology papers are not reproducible. So this is all right. Occasionally there were publications that were a little more hurtful, to be honest. But also the field reacted relatively quickly. So Lisa Feldman-Barrett, a noted emotion psychologist, wrote in the New York Times a piece titled "Psychology is Not in Crisis." Also, the American Psychological Association published a piece saying something similar, and both made a similar claim, namely that a replication of these studies is not always expected because it's hard to do an exact replication. Often small things, sort of ephemeral things, will be different between one study and its replication attempt, and these might be important differences. They might moderate the effect. So these hidden moderators could explain why results don't replicate. I have two things to say about that. One is that I find this a somewhat problematic claim because you're making a strong argument against the robustness of results. I feel that results should be robust against small variations, especially if qualified researchers try and replicate your result. But secondly, I think it might be unnecessary because there is a different thing going on yet. And something that nobody really doubts is going on. Sufficiently many people think this is important that two people have mentioned the issue before me today, and it's only 9:30. It's the issue of publication bias. So what is publication bias? There's a simple sort of informal definition, which is a differential publishing rate between positive and negative results. Journals and others tend to prefer results that are positive, and usually positivity is defined in the sense of showing statistically significant results. In the John Oliver sketch that we watched yesterday, nothing up with acai berries is not an interesting claim for journals to make, and journals would want to publish things that are going to be cited and that are going to help them along. Lest I offend people, obviously not only journals are responsible for publication bias. Researchers will more often than not self-censor, but I imagine a lot of the self-censorship is due to the expectation that non-significant or negative results will not be published. Of course, researchers themselves also have an incentive to publish things that are mediagenic. A slightly more, an interesting take or an interesting way of putting this is by Young et al., where they say the small proportion of results that end up being chosen for publication are not representative of our experience in the lab and of our repeated samplings of the real world. And this is consequential, it's concerning, and it's a bit of a rising concern. The fact, at least, that there exists apparently some large number of well-designed studies that actually do contribute information to a topic, but that don't find significant differences and are therefore less publishable. So I personally would be interested in seeing a well-designed study with a large sample that somewhat conclusively can say that acai berries are not bad for you in any particular way. I imagine there are farmers in Brazil who feel similar. But we agree that this is an issue. It continues to happen. And part of why I imagine this continues to be the case is that as researchers, at least, we do not have any particular power over publishers. Or we have very little power over publishers. I think of the relationship between authors and publishers a little bit as the relationship between an employer and between an employee and an employer who doesn't afford many protections. The publishers hold, to some extent, the key to our promotions, our access to funding, and in some cases our livelihoods. And this is it's a hard position to negotiate from, even though there are attempts. It's also not a new issue. Rosenthal wrote about the issue of publication bias and what he calls the file drawer effect in the late 70s. But even in the late 50s, a statistician named Theodore Sterling wrote a very short, sort of cute paper, and you should read it. It has some flaws. It's not perfect, but if you read the paper, the horror sort of drips off the page, and it feels like he's writing a letter to a friend saying, did you know some journals are apparently selecting what they publish based on p-values? This is terrible, and this is going to cause a literature that's riddled with false alarms and lousy with things that will not replicate. That was 60 years ago, and here we are. So I have a slightly different view of how we should consume the literature, how we should be intelligent consumers of the research literature. As researchers, so we are used to analyzing the data that exist in our lab because we have a particular view of how those data are generated, and knowing how data are generated is critical in knowing how to analyze them and how to interpret results. But published data, by virtue of being published, are notably different from lab data. So you might be naive and believe that published data are the result of some well-documented experiment, the one described in the paper. But that's not true. Published results are the result of a more complex process. It's a combination of the empirical data collection and some socio-psychological process that we call scientific publication. So a filter happens. And if we then treat published data the same way we would treat the data we find in our labs, we are making an error. We're making a statistical error. We're using models and assumptions that we know to be false as the basis of our statistical analysis, even implicitly. And it's not a radical claim here, I think. Instead, we should use the properties and the sampling distribution that is true and not one that is false. So the appropriate set of assumptions is something that takes this biasing process into account. So it's a joint model, a combination of the data collection and a censored publishing process. And I'm just going to show a few ideas of how we do that. So the idea that published data go through the censoring process is not particularly new. It's the basis of Larry Hedges' treatments of publication bias, and Susie Bayari did some work on censoring models. So we can think of four possible ways. I can think of four possible ways that the publication process could bias results. And you can show them, or you can visualize them like this. There is a particular censoring function that tells you the relative probability that negative versus positive results will get published. Right? And you could be terribly naive and say negative and positive results are equally likely to be published, So this relative probability, or this ratio is 1. And if that's true, and you do a simple experiment, then what you need to do is consider the sampling distribution of your data. So if you were to do the experiment very many times over again, what would be the distribution of data, assuming that there's no effect, so that would look like this, assuming that there's some effect, that would look like this magenta distribution, which is very similar, it's just shifted one way or the other a little bit. So that's a naive idea. And if you're naive, what you'll do is you'll compare this model to that model, and if this one is better, you'll conclude there's an effect, and if the other one's better, you'll conclude the opposite. You could be very pessimistic and say results only ever get published if they are positive. And then what you get is a censoring function that looks like this. So positive results, again, typically defined as statistical significance, or a p-value less than 0.05 in many cases, not always. So then a censoring function might look like this. If you get a significant result, the ratio is 1. If you get a non-significant result, the ratio is 0, and you will never, ever get published. If that's true, you get this funny sampling distribution that's different from the one in the lab. So that if that's true, the distribution of t-values, or the distribution of data in the literature, should have this funky-looking distribution that is only the significant bits of this original distribution. And if there is some effect, it'll shift in one direction or the other, and the tails will no longer be equal. Of course, this is not true. Occasionally, we get to see non-significant results. So we can go on and say, well, let's instead say that there is some probability that negative results will get published compared to positive results. Oops. The probability is simply not 1. We'll just call it some variable pi. And if that's true, then under the null hypothesis, the distribution of data that gets published should look like this funny-looking distribution. So the significant results are overemphasized, but the non-significant results still happen. And similarly, if there is some effect, the whole thing shifts. And there's a fourth idea I have, which is a little bit more complicated. It basically says that significant results still get published at a high rate. Non-significant results still get published with some probability, but the probability depends in some way on how bad the non-significance is. So somebody yesterday, I believe, showed some examples of how researchers will show that p-values that are just non-significant will still be treated as if they were significant, and then you read things like these data were trending towards significance or whatever. Somehow they never trend away from significance. But this model it has the same idea. So that sounds like a nice sort of academic exercise. So what, right? Because we don't know which of these processes is active, or at least we don't know right now. But it turns out you can be clever about this in a particular mathematical way. You can think of all these four processes as one big model, right, where there is some other variable that tells you selectively which of these processes is going on. So you would call that variable an identity variable or an indicator. And in this case, you would say the identity of the censoring function is unknown. But I will argue, except to me and maybe a handful of people who are probably in this room, the exact censoring function is not actually of interest. What is of interest is whether the hypothesis tested is true. So whether the null hypothesis or the alternative is true. And you can, I'm not going to go into details, but you can do math to it, and you can integrate out the identity of the censoring function. So essentially what you're doing is you're averaging over all these various possible censoring processes, and you're using a weighted average that gives more weight to processes that are more likely given the data. That is the idea. The method's called Bayesian modeling averaging. And then what you can do is you can calculate a mitigated measure of evidence. So in the same way that we have a measure of evidence to discriminate between the null and the alternative distribution before, you can now calculate a similar measure that takes into account the probability that publication bias is a contributing factor. I sometimes say possibility, but it is. You should just account for it. And this allows you to, or allows us to reinterpret the data in the reproducibility project psychology, because we know that all these original studies were subject to publication bias because they went through the publication process. So if we ever compare these target papers to the replications, when calculating the evidence one way or the other, we should take into account this possibility. On the other hand, the replication set itself, we know has not gone through this publication bias process because everyone said in advance, these are the things we're going to do, and all of those things were published. So no mitigation is required in that case. And if you do that, you can build this horrifying picture. It's horrifying not because the news is bad, but because it just looks ugly. I made it. So what you have here is for a large fraction of those 100 studies, again, the ones for which things were easy to calculate, but I don't think this causes any particular bias. We can talk about that later. For all of those studies, you can plot the amount of evidence favoring the alternative over the null hypothesis in the original study, which is on the horizontal axis, and compare it to what's in the replication study on the vertical axis. And this plot looks a little funny because you might immediately expect, well, these should be on the first diagonal. You would expect there to be a line here, right, if everything went according to plan. That's not what you should expect, for a reason that's a little unfortunate, which is that in the replication project psychology, the sample sizes of the replications were not the same as the sample sizes in the original studies. They had a particular reason for this, but that means that the amount of evidence is the evidences can't be directly compared, because obviously if you collect more data, you're going to have more evidence. What you can compare is evidence between two studies that have similar sample sizes. And that's what the circles are for. So these circles indicate the relative size of the replication sample compared to the original. And now what you should expect is circles that have similar sizes should fall on a line if everything goes according to plan. And that turns out to be the case. You can, do I have nice colors here? Yeah, there we go. So these are studies in which the replication sample was larger, and these do seem to fall on a line. These are studies where the replication sample was smaller. These do seem to fall on a line. And these here are studies where the replication was similar in size, these circles here. And with a charitable interpretation of what it means to be a line, you can imagine sort of a cigar-shaped distribution here. So these are somewhat expected results that kind of make sense. The negative spin, to use that word, in this particular case, is that this section here that I've marked in blue are data sets where the amount of evidence is quite low. So what you call low or high evidence is a little arbitrary, but by my exacting standards of evidence, this chunk of studies here provide only a relatively modest amount of evidence, which is bad news because these were studies done according to essentially the state of the art, and these sample sizes turn out to deliver, like I said, only modest amounts of evidence, which indicates that perhaps we should reevaluate what constitutes a decent sample size for these studies. The more positive message is, on the one hand, these areas would indicate contradiction, where one study would conclude one thing and the replication would conclude the other, and these areas are empty. Right? So we expect that line, we expect that line, we expect that line. So what all of this does is, once you've accounted for publication bias through one of these methods, it almost doesn't matter which one, what you're doing is raising the evidence bar for studies. Because once you've accounted, so what I have here on this graph is the amount of evidence in a study. This is only for the original studies. Are the little dots are the amount of evidence in a study, and the lower end of the arrow are the amount of evidence once you've accounted for publication bias. In all cases, the amount of evidence goes down. It has to. It goes down by a relatively constant factor. This is on a logarithmic scale. So if you account for publication bias, the evidence simply goes down. And you have to account for publication bias because we know it to be present. And there is a simple conclusion here. Publication bias destroys evidence. It costs evidence. And if anything, the reproducibility project in psychology emphasizes evidence is precious. Even these these state-of-the-art studies that get published in decent journals contribute relatively modest amounts of evidence. Now, we know this as scientists. We know that you don't hang your hat on a single study. You integrate across studies. But it emphasizes, at least, that evidence is something to take care of. And the evidence in the reproducibility project doesn't indicate any inconsistencies. It only indicates that there's sort of small amounts of evidence in most studies. Now, obviously, if you have small amounts of evidence, it's easy to avoid inconsistencies, right? The easiest way to not contradict yourself is not to make any statements. But still, the evidence doesn't indicate any inconsistencies. In general, also, the evidence goes in the same direction. So rarely does the evidence go in the opposite direction. So there's almost no instances of data pointing to a significant effect in the opposite direction from expected. That's possibly not a high bar. But in order to explain the results of the reproducibility project, this is me coming back to the statements by APA and others, you don't need to assume these hidden moderators. Even if there were no hidden moderators, this is roughly what you would expect. And about evidence in the reproducibility project, obviously it'll depend on. My screen just went black here. Okay, I'm going to do this. So evidence in the reproducibility project obviously depends on the sample size for obvious reasons, right? Each observation carries some evidence. For another reason that links back to those recommendations John Ioannidis made at the very end of the last talk when he was mentioned, people use sort of standard statistical methods and off-the-shelf analyses a lot, and to their own detriment. You can use more model-based analyses to obtain more evidence from the same data. But critically, I think publication bias damages and decreases evidence. For an obvious reason, some presumably good work goes unpublished, but for a less obvious reason that if you take into account the fact that a particular paper went through a biasing process, this decreases the amount of evidence even in the published paper. Right? So even in the things that do get published, the evidence is damaged by this biasing process. And there's a number of things you can do. So I was asked at some point to draft a chart for a research program that would address this. I'm not going to go through all the details of this. What I want to show you is that, and other people have said similar things, there are different branches to who could contribute to the improvement of robust and replicable results. There are three branches here. The one on the right is sort of society and institutions and funders and publishers. The middle one would be particular methodology research groups. So this would be me. And on the right end, which is what I want to focus on a little bit first, is individual researchers. So what can you do in your own lab to increase the replicability of your own research? And one thing that's going to be useful and is not widely recognized, I think, in empirical fields, is there was a philosopher, mathematician, and logician at the end of the 19th century called Charles Sanders Peirce, who was named at the time as, or named now as one of the most original thinkers of his time. And he proposed a set of rules for how you should evaluate scientific hypotheses. And his first rule is very strict, and is so strict that it's not exactly feasible. He says any hypothesis you test should be sort of distinctly put as a question. That seems obvious. It should be made before you make the observations that you use to test its truth. So you should make predictions. So you should always do confirmatory work where you say in advance, I expect that this is going to happen and this is how I'm going to test it. And you should do so before you have the data. That's rule number one. And the second rule is that this also seems obvious, but this is contradicted by the presence of publication bias. Failures as well as successes should be honestly noted. So a rule that I've proposed elsewhere that sort of combines these two is what we call the no more bets rule, which basically states that if you're going to test any hypothesis or do any experiment, you should decide before you've collected any data point whether you're going to submit this for publication. This seems obvious, but it's often not. It's a little murky in an empirical lab to decide between which data you are currently collecting are your pilot data, and which are the data that you're going to actually base your conclusions on. It shouldn't be, but it often is. But if at some point you've done all your pilot studies and you know how you're going to do the experiment, you can call no more bets and say the next run of trials is my real experiment. This is obvious in some fields. It's not obvious in others. Further, in order to address the high cost of evidence, you could, and this is a personal theory, and some other people have mentioned similar things, you could adopt a habit of testing theories through randomized designs. So people will mention these hidden moderators as possible reasons for why something does or does not replicate. And you don't technically need them to explain the discrepancy in the replications in the reproducibility project, but they might genuinely exist, and they presumably do. And there's no reason why researchers couldn't vary these moderators continuously and constantly in their labs. Making narrow statements is slightly easier, but robust statements are perfectly within our reach. I've mentioned this. I think people should use custom statistical models more than off-the-shelf ones. You can get more evidence out of the same data using a more appropriate analysis. Consider formal quantifications of evidence. This also seems obvious, but people don't often do this. People use decision rules to decide whether there is enough to go on in a data set. That's for the empirical researchers, and on the other side, there's some message, I guess, to academic publishers and funders, what you could do to address this. First of all, again, an obvious one is, and other people have said this before me just today, publication decisions within a journal should be based on the quality of the design and the ability of an experiment to adjudicate between different theories rather than the outcome, because deciding based on outcome is makes you a newspaper, essentially. And similarly, if you're an institution, I'm trying to argue a little bit for this, at least at my own institution, that you should prefer, for the purposes of personnel evaluation, publications that are vetted by quality rather than by luck of the draw. And further, and again, people will talk about this later today and tomorrow, publishers and funders currently do, to some extent, and should continue to promote open science, and do something that I've called formation of ad hoc research consortia. So other fields outside of social sciences sort of automatically work in consortia because data is sort of hard to come by, or you need large amounts of data to make a statement. In social science, this isn't particularly common, but what you could do as a journal or as a funder is assume some sort of stewardship over a particular topic and say, if there are people who want to work on this topic, we can use the infrastructure of the journal to work together and to organize who contributes to this. There's a couple of different models under which you could do this. But I feel like publishers already play a variety of parts and have a variety of roles in the academic world. And I changed this bullet point from try being a force for good for once into adopt intellectual stewardship, which sounded more positive. But I genuinely believe that there is a role for publishers to play a role in collaboration with researchers, where now it often feels like there's this antagonistic relationship, and there's no need for that to be true. That's the extent of what I wanted to say today. Here are some benefactors I wish to acknowledge, and there's a list of references here. Thank you.